Alright guys, welcome to lesson 9.5. Today we're going to learn how to solve equations that have logarithms in them. So first of all, let's talk about the domain of a logarithmic function. First of all, you guys might want to remember what a domain is. The domain is all the possible values of the input variable. Whenever you have log functions, they're always going to have some kind of a base right here. The x is usually going to be located here, and the y is the output. So the input is here and the output is here. Now, domain is all the possible values of x. In other words, what are you allowed to plug in here? Now, as you guys might recall, we've learned in other lessons that this number must be positive. Now, I don't want you guys to think that that means that x has to be positive. For what I wrote right here, yes, x has to be positive. But what has to be positive is whatever the argument is. Now, the argument may be x, or it may be something with an x in it. But the point is whatever's right there has to be positive. And the way we write that is that the domain is all the possible values of x which allow the argument, the letter b there, to be greater than 0. In other words, positive. Okay, so let's go ahead and take a look at some examples here to help this make sense. Example 1 asks us to find the domain for this logarithmic expression. So this piece right here is like my b value. It's called the argument. The argument has to be greater than 0. In other words, it has to be positive, because that's what we're taking the log of. And whenever you have a log, whatever's right there has to be positive. So 5x minus 10 has to be greater than 0. That doesn't mean x has to be greater than 0. That means that this has to be greater than 0. So to find out what x is, we have to solve for x. And it turns out that x has to be greater than 2. So as long as x is greater than 2, we have a function. Now, we haven't talked about graphing logarithmic functions yet, but just so you know, the graph of this function would probably look something like this. There's an invisible line here, a vertical asymptote. This function can't exist at 2 or anywhere behind it. It has to be in front of it. X has to be greater than 2. So every point, every value of x has to be greater than 2. So that's what that means. Now, you guys don't need to worry about the graphing stuff. We're going to get to that later. For now, all you need to know is that the argument has to be greater than 0, and solving for x tells us what the domain is. The possible values of x are, x can be anything greater than 2. Let's go ahead and take a look at number 2. So in this case, my argument is 6 minus 3x, and it has to be greater than 0. Now, something interesting happens on this one as we start to solve it. Something that's easy to forget about. But when you're solving an inequality and you divide by a negative, we have to reverse this sign. You might want to make a little note of that. So dividing by a negative, reverse the inequality. That's an old math rule from a while back. So anytime you're solving an inequality and you divide by a negative, you have to reverse the inequality. So in this case, the domain is x has to be less than negative 2. All right? So let you guys try 2 of these. So go ahead and pause the video here, give these a try, and see what you get. All right? So there are your solutions for 1 and 2 in your student practice. Let's go ahead and move on now. So we're about ready to move into solving logarithmic equations. And when you solve an equation, you get a solution. Okay? But sometimes with logarithms, there's these things called extraneous solutions, which are not solutions at all. So let's talk about that. First of all, some functions have restricted domains. Square root functions, rational functions, and logarithmic functions. What do I mean by a restricted domain? That means that x can't just be anything. X has to be a certain number. Like on the last slide, we saw that x had to be less than 5, for instance. So x can't just be anything. X is limited. In other words, it's restricted. whenever a function has a restricted domain, and you're solving an equation that has one of these types of functions in it, it's possible that your answer that you get isn't part of the domain. So for instance, on student practice number 2, we saw that x has to be less than 5, right? But let's say I was solving an equation and I got something like x equals 10. Well, that's not less than 5, right? That's what we would call an extraneous solution. It's a false solution. Sometimes when you're going through the steps of solving, we use laws of math to solve equations, but sometimes those laws are making assumptions, and those assumptions may not be true. And so whenever you have functions that have restricted domains, it's possible that you'll get an answer that's not in the domain, and that's called an extraneous solution. We've seen it before earlier this year when we did square roots. We also saw it when we did rational functions. And now we're seeing it again with logarithms because they have restricted domains. Let's go ahead and take a look at example 2 here. These are basic log equations, and we're going to start off here. All right. So for step 1, the first thing we want to do is we want to find our domain. We want to make sure that our answer that we get doesn't go outside of the domain. Well, in this case, for step 1, my domain, we'll call this A, can be found by taking your argument and making it greater than 0. And that's it. I don't have to solve for x because it's just x this time. So long as the answer I get is greater than 0, then it's a good answer. If I get anything less than 0, it's not a good answer. Okay? All right. Step 2. We're going to exponentiate both sides. Now that's a new word for you guys. You may not know what it means, so I'll show you what that means. Okay, so suppose you have a log with some base here, put an x here, and some number over here. We'll call it c. All right. To exponentiate both sides, what that means is we're going to write both of these sides of the equation as a power of this base. So that would look like this. All I did was make each of these sides a power of the base that's right there. Okay. Now, why do we do that? The reason that we do that is because this and this cancel. We saw in our log properties earlier this year, and we get x by itself by doing that. So let's go ahead and take a look here then. And number 1, we have log base 3 of x equals 4. All right. So I want to exponentiate both sides. So my base is 3, so it's going to be 3. And then I'm going to put this whole log expression up here. And it's going to be 3 again, and then the 4 goes here. And what happens is that this and this cancel each other out, and I'm left with x equals 3 to the 4th, which is 81. And so there's my answer. I got x equals 81. You want to check your answer. Make sure that it's in the domain. Is this answer greater than 0? Yes, it is. So we're good. That's my solution. So step 1, find your domain. That way, at the very end, we can make sure that our answer is allowed. Step 2, exponentiate both sides. Step 3, check your answer to make sure that it's part in the domain. All right? If it's not, we would have to throw it out and say, oh, well, that's a extraneous solution. Let's go ahead and take a look at number 2. So let's do the domain. Once again, it's x is greater than 0. Step 2, we're going to exponentiate both sides. So look at this expression. What's the base? Hopefully you remember that when they don't have the base written here, that means it's 10. So I'm going to make each of these sides a power of 10. So it's going to be 10 log x power 10 to the second power. On the left, these cancel each other out, and on the right we have 10 squared, which is 100. Is that number greater than 0? Yes, it is, so that's my solution. So, 3 steps. Domain, exponentiate, check your answer. Let's do one more. Part 3. Once again, we have the same domain. Now, it's not always going to be this, just so you guys know, in the problems that are going to come up in the later examples that I do in this lesson. It's not always going to be x is greater than 0. You'll see why. But for these 3, which are the basic ones, we're going through, it is. Part B, we need to exponentiate. Now, when you have an ln, what base are you dealing with? That's a base of e, isn't it? So to exponentiate both sides, it's going to be e to the power of ln of x on the left and e to the power of negative 9 on the right. These cancel out. Now, you can leave your answer like this when it comes to e. I think that would be fine. Or you could write it like this. But I think getting a calculator out and finding out what e to the 9th power is a little bit overkill and not necessary. I think we can leave it like that. Okay. Either one of these, though, are good answers. Why did I write this one? Because when you have a negative power, that means you can move to the bottom with a positive power, right? Okay, so that is what I would consider to be the most basic types of log equations where we're solving for x. So let you guys go ahead and practice a couple of these. So go ahead and pause the video here and try these out. And when you're all done, unpause the video and check your answers. And we'll move on from there. So there are the solutions. If you wanted to change this into a decimal, you could. 7 to the 1.5 power. I'll go ahead and punch that in my calculator real quick. But I think it's okay to leave it like that, too, just because either way it's an awkward looking answer. But about 18.520. Okay. All right, let's go ahead and move on. So for the rest of the examples I'm going to do today, they're just going to be random types of log equations that you can see. Each one I show you is going to have something a little bit different in it. So after I do one, I'll let you pause and practice one like that before we move on to the next. Okay? All right, so let's begin. This one has a p here instead of an x, but that's my argument. So for step A, let's check our domain, right? My domain is p has to be greater than 0. Step B, we want to solve this now. And so on this one, we want to get rid of the outside numbers first. By outside numbers, I mean the numbers that are not in the logarithm. So in this case, that would be the 9 and the 2. So I'll show you what I mean by that. I want to get this log p all by itself. So I need to get rid of the 9 and the 2. So the first thing that we're going to do is we're going to move this 9 over like that. The next thing I'm going to do is I'm going to divide both sides by a negative 2. That way I have this. Okay? Once you have the log by itself, I guess another way that I'd probably like to word this is instead of get rid of the outside numbers, let's say get the log by itself. I like that better. Get log by itself. So in other words, that still means the same thing though. Get rid of the 9 and the 2. After you get the log by itself, then you can do the same thing we did in the last problems, which is to exponentiate both sides. So we have log p of 2. So what base is that, you guys? What base is log p equal to 2? Well, that's a base of 10 when they don't write the base. So that would be 10 to the power of log p is equal to 10 to the power of 2. And these cancel out. And this equals 100. And of course, you still want to, at the very end, check your answer to make sure that it's in the domain. T equals 100. Is it greater than 0? Yes, it is, so we're good. That's my answer. All right? Let's go ahead and have you guys try one like that. So go ahead and pause the video here and give number 2 a try. When you unpause the video, you'll see the solution. So there's our solution. E to the second power is the answer. My argument R has to be greater than 0. That's my domain. Step 2, we want to get the ln by itself, the logarithm. So we minus 6 and divide by 5, which gives us this. From there, we're going to exponentiate both sides by making each side a power of the base e. And then since these cancel out, we're left with our final answer, which is greater than 0. E to the second power is greater than 0. How do I know that? Hopefully you guys remember that e is like 2.7. If you raise 2.7 to the second power, of course, that's going to be greater than 0. All right. Let's go ahead and take a look at another one. We'll call this example 4. All right. Now, what makes this particular problem different? You'll notice that my argument is more than just a letter this time. The stuff that is being logged is multiple things. So in this case, that's going to change part A a little bit. Instead of just saying v is greater than 0, now we have to have negative v plus 3 is greater than 0. Oops. And look at that, I'm dividing by a negative. You guys remember what we have to do when we divide by a negative? You have to flip that arrow around. So my answer, if I get my answer, has to be less than 3. I'm not allowed to get an answer for v that's less than 3, because otherwise it would not be part of my domain and it would be an extraneous solution. So there's my domain step. Step 2, let's get the log by itself. So I want to get this by itself, which means I want to get rid of this 4 here. So to do that, I'm going to add 4 on both sides. And now I've got my log by itself. Now some of you guys may be thinking, Mr. Bailey, why is the log by itself? It still has other stuff with it. Well, the log should have a base and it should have an argument. And that's a whole construct of a log there. So that's all that I mean when I say get the log by itself. All right, now, step C, we're ready to exponentiate. 9, started making that with an A. All right, so we're going to exponentiate both sides. My base this time is a 9, so it's going to be 9 to the power of log base 9 of negative v plus 3, and 9 to the power of 1. And these cancel, of course. 9 to the first power is just 9. And we're going to solve this equation. And I get v equals negative 6. So let's, before I circle that and call that my answer, let's check it. I get v equals negative 6. Is that less than 3? Yes, it is. So that's a good answer once again. It's not extraneous. That's a good solution. All right. So let you guys try one of these ones. Go ahead and pause the video here and try student practice number 4. When you unpause it, you'll see the solution. All right. So final answer there is 626 over 5. I'll let you guys go ahead and pause the video here and check your answer and see if you agree or not and why you may have some disagreements. But anyway, we'll go ahead and move on to the next one, example 5. All right, here we go. So this one's interesting because we have multiple logs in it, and in fact there's logs on both sides. And just as a warning to you guys, these are the ones where extraneous solutions happen a lot. It doesn't mean that it will happen. I'm just saying it can when you have a log on both sides. those are the types of problems where an extraneous solution is pretty likely. So let's go ahead and begin. Now you'll notice that we have two different arguments. I've got one argument and I've got another argument. So for the argument on the right, I know that x has to be greater than 0. From the argument on the left, negative x minus 10 has to be greater than 0. So let's go ahead and solve this one. So x has to be less than 10, negative 10, and also greater than 0. Now, you guys that may be causing you to pause for a minute and think, wait a minute, how is that possible? How can a number be less than negative 10, but also greater than 0? And the answer is, well, that isn't possible. And so therefore, I already know that this thing is not going to have a solution to it. Okay, it's not going to work. But I'm going to pretend for a minute that I don't know that, okay? But if you notice this right away up front at step A, then you can just stop and say, okay, well, there's no solution to this because it's impossible for something to be less than 10 and also greater than 0 at the same time, all right? But let's just pretend for a second that's not like that, because if you do end up with something that's possible here, you have to go on to the next step. And the next step is kind of interesting. So if you ever have log of blah blah equal to log of blah blah, what you could do is you could just cross off the logs. Okay, what do I mean by that? Well, anytime you have an equation, you have the same thing on both sides, you could just take it off and the equation stays balanced. So for instance, if I have log base 2 of negative x minus 10 is equal to log base 2 of x, well, since they both are a log base 2 on the left and the right, we can just get rid of that. Okay? And then from there, you would just solve what's left. Now remember, we're going to get an answer out of this, but it's going to be an extraneous solution. Because we already know from step A that this is impossible. But I'm just pretending that it's okay for now, because it may be okay. You have to go through and solve it, and it'll work out fine. Let's go ahead and do this one. So we have negative x, well, and the answer here is just to solve at this point. So negative x minus 10 equals x. I would go ahead and just add this x on both sides. I get x equals negative 5, but before I circle that, I better check to make sure it's okay. And this is where you guys should notice there's a problem. I get x equals negative 5. Well, is that greater than 0? Nope. Is it less than negative 10? Nope, it's not that either. So this is what we call an extraneous solution. It's not part of the domain. Okay, so there is no solution to this problem. Now, once again, we could have noticed that from part A, because this is impossible anyway. It's impossible for x to be both greater than 0 and less than negative 10 simultaneously. And so there's no way you're ever going to find an answer that will work for this side and this side. They just don't agree with each other. But sometimes you'll find that double domains can have some agreements to them, and you're going to need to go through the rest of these steps anyway. So those steps are to cross the logs off of both sides and then solve what's left. And of course, don't forget to check to make sure that it works for both domains at the end. And it has to work for both. It can't work for just one of them. It has to work for both when you get an answer. All right, so let's go ahead and have you guys try one here. Pause the video and try number 6. When you unpause it, you will see the solution. So here's part A. I've got my domain for the left log and my domain for the right log. The domain for the left says that x has to be greater than negative 2. The domain on the right says that x has to be greater than 1.5. Can you guys think of a number that's greater than negative 2 and also greater than 1.5? Yes. Basically, anything that's greater than 1.5 will work for both of them. Because if it's bigger than this number, it'll also be bigger than this. So long as our answer is bigger than 1.5, then we're in good shape. So let's go ahead and I'll pause the video and let you guys do steps B and C and D. And then you can check your final answer. All right, for step B, We can just drop the log off of both sides. And then for step C, we solve for x minus the 2x on both sides. Add the 6 on both sides and divide by 2. And we end up with 5. And is 5 greater than 1.5? Yes. And is 5 greater than -2? Yes. So that's a good answer. So this one was not an extraneous solution, and it actually does have a solution to it.